and this is the one that I'll go over, is the Gauss-Seidel method, which is one of the homeworks that I'd ask you to look at. And then after today, we will be moving into interpolating polynomials. So it's an extension of what you've kind of picked up on over the last few weeks. And we just kind of keep right on going. We don't backtrack here. There's just too much to throw or to get in to the course here that you need to know or to be familiar with. All right. Let's see if this will work. Hey, there we go. All right. So we're still doing linear algebraic equations. This is, how many of you use MathCAD, by the way? All right. But I noticed you were doing, Jacob, did you do?
I use MATLAB.
You use MATLAB
on the side to check things.
Okay. Yeah, well, this is an example of a MathCAD solution of the bisection method. Actually, this is the MathCAD file that we used, for example, for last year's problem, where we had a simple beam, simply supported beam. And so this is still the bisection method. It's kind of like what you were doing on the problem, maybe a little bit last time, just slightly different based on the constraints of the problem. But that's what a MathCAD file would look like, and then these would be the results that would come out. So for those of you that are big on MathCAD, we'll leave these in the slides, or if you're interested in using it later on or so, then there it is. Okay, iterative technique. They're popular, they can be efficient. They're easy to establish. They do require less computational storage. That's the advantage of them, but you have to be careful because sometimes they can be costly versus, say, a Gauss elimination or what we call direct methods. Right? Okay, so the Gauss-Seidel method is the most commonly used iterative scheme. So here we have a 3x3 matrix. So AX equal to B. That's what you've been solving, right? The unknown is X. You solve for X1, X2, and X3 by solving this set of simple recursion relations. So if I have a 3x3, that would be the exact statements that I would be solving for the unknowns. And so what I'm doing is I start with some initial guess or a value. I say, okay, let me try running it. Let's see what I get. Maybe my error criteria, the difference between the new and old value, maybe it's too big. I keep going until obviously it gets very small and I say that's good enough. All right, a lot of times we assume 0 as an initial guess. If you have an idea about what the answer would be to begin with, go ahead and put that in. Maybe it takes 2 iterations. You know, maybe it takes you know, a lot of iterations. You just don't know. Okay. Okay. What we're going to do is figure out how this thing. Let's see what this does. Oh, okay. Okay. All right. Jacobi iteration. Iterative scheme based on the following algorithm. So remember, these things are called recursion algorithms, all right, or recursion relations. And so it means, okay, this is what I would write out in kind of like pseudocode or so. And so if I plug in the values for whatever the rows or the columns would be, that would be the statement that I would be solving for. That's what you would plug into MATLAB or MATCAD or Maple or whatever. Okay. Values denoted by superscript, n+1. They generally are referred to as the unknown values, right? They set on the left-hand side. Known values would be the n's, all right? So known values are previous values, are designated with that superscript. Okay, Jacobi iterations, very simple, can be set up for parallel processing. However, the method's slow, and in some cases it can actually diverge on you. It was commonly used in fixed point iteration to find roots of an equation, here in the case where this thing may diverge. All right, it is important that AII, now what's the AII mean? The main diagonal value, all right? Cannot be 0, obviously. Just looking at the recursion relation. You would have big problems, right, if it did that. So you have to ensure that you don't get a 0 division in that. Gauss-Seidel iteration. Now let's look at the difference. There's a subtle difference between Jacobi and Gauss-Seidel. Anybody pick it up? Take a look. What is it? See right there?
Is it because X has an exponent?
It's not an exponent. That's an indicator. Okay, mathematicians, what's the problem here? Or is there a problem? Say that again.
There's unknowns on both sides of the equation.
All right, but you're going to capitalize on the fact that a computer is relatively stupid. And so it's going to use the previous value it just calculated instead of the previous iteration. It's going to use the value it just crunched, and it'll go in there. All right? So you can actually have the appearance of having two unknowns in that equation, but the computer is going to say, I'm updating all the time. So you're going to capitalize on that. Okay, so let's take a look. Just calculated value for x is used in the recursion algorithm, but not for values that have been calculated as yet. So it's updating the most recent value instead of from the previous iteration in those values. That's a big, big difference. All right? Significant improvement in Jacobi iteration. Right? Take advantage of the ignorance of computers. Whatever it was just calculated, unless you tell it otherwise, it's going to use just what it calculated. All right? This technique can also suffer from slow convergence and can diverge. You have to be a little careful. You have to ensure that you have diagonal dominance. So let's see what this says. Diagonal dominance, AII, right? Absolute value must be greater than the sum of AIJ. What's this mean?
The position matrix.
The rows. The row in which that diagonal term appears. See, J not equal I. All right? So you have to ensure that that is diagonally dominant. Yeah, Aaron.
With the Gauss-Seidel iteration, you basically just, you calculate for, plug in some guesses for the two other, in the case of the 3 by 3.
Yeah.
For the two other x's, and then you solve for the first, and then you do that. for
Yeah,
all
you're
three.
initializing with whatever you say, let's start this thing. And then it's going to start incrementing as it keeps working its way down. in the
So
solution
you
sequence.
just keep trying to solve for
You're
x's.
just, see, you're constantly replacing the value with the value you just calculated, right? Yeah.
I'm not understanding what diagonal dominance means, sir.
Okay, remember, you have a main diagonal,
Right?
that would be the AII, correct? Okay, so within each row of the matrix, you want to ensure that that value is greater than the sum of the rest of the coefficients in the row.
So this method will not work unless main diagonal is greater than,
You must ensure that you have diagonal dominance.
Can we do
So-
that by?
If it's going down like this number has to be greater than all
Yeah.
the rest of the numbers added together?
That's what that means. Greater than the sum of the absolute values of the other row values.
Is there some pivoting method that allows you to do that?
That's what you can do, sure. That doesn't mean, oh, we can't do it because this technique isn't any good. Right, sure, you can, there are all kinds of little tricks for the trade that get embedded into the more advanced algorithms. Okay? Okay, let's take a look. The difference between Gauss-Seidel and Jacobi iteration. A, B, first iteration. All right, so here's x1. All right, so we calculate x2 based on, there's x1. We go down here, there's the value from x2, goes into their second iteration. Okay, we come down here, okay, here's x3. We're calculating x1. Well, I think you can see the flow chart, right? Pretty evident right up here. Okay, see what happens. Here is x1, x2, x3, okay? A, Gauss-Seidel, B, Jacobi iterative method. All right? What's the difference? I just calculated x1, I throw it into there. I just calculated x2, I throw it into there. All right? Otherwise, I have to use whatever I set up initially, calculate all the values, and then start over again. All right? To the next iteration. That's the big difference. All right. Here is a Gauss-Seidel in MATLAB environment. So I have, here's a 3x3. So I'm calculating x1, x2, x3. This is what the recursion relation would look like for just a simple 3x3. Remember, if I have a 10x10 or a 20x20 or whatever, I use IJs, right? Okay. I can express it in matrix form, so it looks like this. All right, so here, see what I've done with the load vector, or the right-hand side, right? So here's this, here are the coefficients that would be in C. Fortunately, you don't have to do this by hand. The computer is doing this for you. All right, so here is a sample MATLAB file for you for doing Gauss-Seidel. Okay, as you can see, it's not too difficult, a little bit longer than what you saw in the past on this, but I think there's enough in there for you to begin to see, oh, okay, all I have to do is load this up with the matrix, whatever it would be. Remember what this is?
Error.
That would be the error that says, okay, if I have anything smaller than that, stop, I'm done. So I'm finished with it. So you could use this as kind of a background to do your own. Okay, nonlinear equations. We've been talking about linear equations. What do you do when you have nonlinear equations? Actually, two techniques. Successive substitution or Newton-Raphson. Where'd you use Newton-Raphson before? Problem number 1, right? I tell you, it's going to keep coming back. All right, successive substitution. You solve each equation for an unknown, then solve iteratively to compute the remaining values. You do that already. That's just straight mathematics. That's how you had to do it in math class. Convergence depends on the manner in which the equations are formulated. So now it gets a little tricky because you can actually diverge here if your initial guesses aren't relatively close to what the true value would be. Okay, I think there was an example I gave maybe a couple of lectures back. You can go through the slides where you saw something that began to diverge because maybe the round off was eating away at it, and suddenly after about 4 or 5 steps it really started getting big. That's a divergence. That's what we mean. All right? So what this tells you is that you really need to analyze the problem that you're solving so that you have that engineering gut feel as to what you think the solution ought to be or the magnitude of the value. All right? A better approach, Newton-Raphson. Has the same limitations as before, right? Remember what we had in there? F prime, the derivative? Yeah, be careful. Okay, remember this, Taylor series. I think right here I had delta x, right? In the Taylor series. And so this just went out in the series as far as the next one, delta x squared over 2 factorial and so forth and so on. That's the delta x. So if I look at this, is that a forward or a backward approximation? You can tell. How can you tell? Right there. I plus 1. X of I, I'm going forward. I plus 1. All right? That's just the difference between xi plus 1 and xi. That's delta x. That's a plus sign. Right? Somebody picked up on that, right? If it would have been a negative, right, it would have been a backward. But I can tell from the I plus 1 that's a forward. So xi plus 1 equal xi minus f of x of I divided by, right? There's the derivative. Okay? That's Taylor's, or that's the going to be the Newton-Raphson. All right, if I have 2 variables, a first order Taylor series can be written for each nonlinear equation. Here's the first equation, here's the second equation. What have I done here? I just carried out an additional term in the expansion. Right, so here, this would be, if I truncated it right here, that's what you would have here. So, if I just add some more terms, you see what I'm doing? All right, so it just continues on and on. All right, I can rearrange those equations, just like we did in the previous slide for the one unknown. So here, for x1 of I plus 1, for the first equation, it looks just like this. Right, all I did was just divide by those terms from the Taylor series. Here's what it looks like for the other equation. All right, it's very simple. In fact, it's so simple that the computer will do that for you unless you basically tell it otherwise. Okay? Find the roots of x1 squared plus x1, x2 equal to 10. x2 equal to 3, x1, x2 squared equal to 57. You have two equations, two unknowns, right? We know the exact answer on this, it's 2 and 3. Okay. Find the partial derivatives, evaluate them at the initial guesses, x1 equal 1.5, x2 equal 3.5. Okay, let's see what happens. Here's the partial derivatives. First equation, all right, with respect to x1, with respect to x2, same for the second equation, all right? So here are the values. The determinant, remember, I have a 2 by 2, right? I find the determinant, it's 156. Now the functions using the first guesses, remember I said, let's use those as the initial guesses, 1, 5. So we just plug those in, F1, F2, here's what we get for the two values. Now obtain x1 for the first iteration. What does this look like? Right? It's a Newton-Raphson. Okay, so here's x1, here's x2. Exact value should be 2 and 3. That's just after one step, right? One iteration. So it won't take very many, right, to actually come up with the exact solution. So here's where the root would be. Here's this equation. Here's the first equation, second equation. That's what you're looking for, the solution where they cross, right? 2 and 3.
You took the partial derivative of function 2. Can you go back to the other slide, sir?
Sure.
You took the partial derivative of the first function with respect to x1 and the second. Okay, and then you just.
Yep. Okay.
Okay, I understand.
See, remember, you're not dealing with linear equations, you're dealing with nonlinear multiple equations. Ratchets up in difficulty quite a bit. All right, now let's talk about some improved iterative techniques. One way to improve this is through what we call relaxation. Okay, relaxation. A new value is calculated, the value is modified, and it's weighted. All right, so what you're trying to do is to accelerate the convergence of this thing. There are basically two techniques. It's either called an under-relaxation or it's called an over-relaxation. What do you think under-relaxation means?
Less averaging?
I'm going to back off of the iteration or the value I get. I'm going to say, wait a minute, I don't want it to be that. I'm going to actually lessen the value because I don't want it to accelerate that fast, all right? Over-relaxation, just the opposite, right? I know, I can probably sense that I know what this convergence is and this thing just wants to get there. Let's help it along. Over-relaxation. This is the algorithm that does that. All right, so the new value is equal to the old value, right? 1 minus this, all right? You see what we're doing? The relaxation factor is the omega. All right, that's the weight. It varies between 0 and 2. If it's between 0 and 1, that's called under relaxation. All right? So if I'm running like 80% or 90%, I would be using something like a 0.8 or 0.9. If I run 1, what is it? There's no relaxation, right? It's just straight iteration or whatever the technique I'm doing. If I run it between a value of 1 and 2, we're over relaxing. All right? So we're trying to accelerate this thing even more so. A classic example of where we use under relaxation is when we're calculating pressure and fluid flow. Right? Generally, you tend to use or want to use an under relaxation on the pressure. Where we tend to use an over relaxation is when we're calculating stream functions. Or we're calculating a steady state Poisson or Laplace equation. And we're saying, oh, I want to hurry up and get the steady state result out of this. We will tend to over relax that solution. Right? Oops, let's go ahead. Successive over relaxation. So an iterative scheme based on the following algorithm. All right, now, new value we want to calculate is the old value. What does this look like? It actually looks like the Gauss-Seidel. All right, all we've done is say, well, we've got a relax, or we've got a weighting function up there, the W. Okay, so if that were equal to 1, what you would find out is that you would have a Gauss-Seidel, right? There's an optimum value for the omega that will produce the least number of iterations. If I use 1 and I'm running a test case, for example, this is actually one of the examples that I think I referred to earlier. It would take 24 iterations. If I change it, if I over relax it to a slightly larger value, 18, 13, 1.3 is 11. What's happened here?
The increase in value is too big of a number.
What's it doing? Okay, this is one of the things you have to be careful about with particularly over relaxation. So what you're doing is trying to determine where's the peak relaxation factor. So what I want to do is to come up with that value that will give me the minimum number of iterations to converge. But if I push beyond it, you notice what happens, right? It begins to go back up. All right, now, you can actually calculate that value for some problems, but not all. And so a lot of times, particularly in the nonlinear type problems, structures, heat transfer, fluids, and so forth, you generally have to do a trial and error. But you kind of guess what it would be, and then maybe a little bit of tweaking here and there, and you'll have a close enough value. Here's how you calculate the optimum value. Here's the formula, all right? All right? So if I'm dealing with a function x and y, then a two-dimensional form of the relation can be used. What's n in this case? Number of unknowns. All right, number of unknowns. Here, number of unknowns, x direction. Number of unknowns, y direction. All right, so you can calculate the optimal value ideally using these formulas, 2D, 1D, okay? They're theoretical estimates. So as I say, you may have to do a trial and error to get it just right. So you may calculate what this should be, but then you find out, oh, it's not quite right. Maybe I need to change a second decimal value or something. Okay. All right, summary of the solution schemes that we've been through. The first, Gauss elimination. All right, I think once you see this, this is a table, I think it's in your book, that can prove to be handy for you in referring back to these various techniques. Gauss elimination, right? You decompose it into an upper triangular and then back substitute. All right. Problems it can have and the remedies that you can do to fix it. This is LU decomposition. What is it that you're doing? You're decomposing it into a lower triangular and an upper triangular. matrix, okay? You then back substitute or back calculate from this, and it gives you your unknowns. All right, here is Gauss-Seidel, right? First step, second step, third step. If I had 3 unknowns or whatever, I'm going to use whatever I just calculated and put into here. Whatever I calculate from here, I'll put into here. All right? What I want you to do, finish reading the chapters on iterative schemes, direct solution techniques. We will be finishing the simultaneous equations or solutions to simultaneous equations. I want you to know how to use direct methods and iterative methods. Next time we're going to start interpolating polynomials. Now, let me tell you, circle Gauss-Seidel iteration. All right? Circle that one because I'm going to ask it again. Circle successive over relaxation. Why? Because I will probably ask it again. All right? Be sure that you can do a simple Gauss elimination. If I ask you in a peripheral kind of sense or not in specific detail, what can you do to improve Gauss elimination? What's the first thing that comes to your mind?
Relaxation.
What's your second thing that comes to your mind? Pivoting. LU decomposition. All right? No, because when quiz time comes, which I think is in 3 weeks, you're going to say, well, what was it that was important?
Also, not having my pop quiz.
No, unless you want one. You don't want one.
Not really.
I didn't think so. All right. Any questions about the homework that you got? Any questions about your homework for next Tuesday that's due? How many of you have worked out the equation?
These Gauss work in the second method for the first one. Because you asked for a Gauss elimination method, so wondering if the Gauss work is acceptable.
If you want to do a method other than Gauss elimination, you have to tell me Gauss elimination, and then you have to also then describe what you're doing as an alternative to Gauss elimination. You understand? So it's kind of like adding more work. You know, but that's up to you. But as long as I know that you know Gauss elimination,
So if we had a pivoting, then it's more like a little side note of that.
that would be fine. Sure. Okay, any other questions? All right, see you on Thursday. Okay.
Only 2 chapters.